This is the last day of our acquaintance. I will meet you later in somebody's office.
Okay, we're going to do another example from 5.5, a procedure for curve sketching. There's nothing new to teach you here. We're just going to go straight to the one example. And you know as well as I do by now that this one example is going to take us a long time. So we're going to sketch this graph. F of x equals x squared divided by 1 minus x squared. So we're going to go through those 8 steps. First step, domain. So for domain, we look for 2 things. We look to see if there's a square root, there's not, and we look to see if there's a denominator, there is. And what needs to be true about the denominator is that the denominator, 1 minus x squared, has to be anything except for 0. So it cannot equal 0. So we're going to solve this inequality here, solve it the same way you solve equalities. Let's move the x squared over. So we know that 1 cannot equal x squared. Then we take the square root of both sides. So we get that x cannot equal plus or minus, because we use square roots to solve this, x cannot equal plus or minus 1. Those are not part of our domain. Step 2 is intercepts. To get the y-intercept, you're going to plug 0 into the x's. So you're going to get 0 squared over 1 minus 0 squared, which is 0 over 1, which is equal to 0. To get the x-intercept, you're going to make f of x equal 0 and equals x squared over 1 minus x squared. You're going to solve that. Let's multiply both sides by 1 minus x squared. So that'll just get rid of this 1 minus x squared, and this will still be 0. So you get 0 equals x squared. Take the square root of both sides, you get x equals 0. So obviously you found it twice actually. The y-intercept 0, the x-intercept 0. In other words, your intercept is 0, 0. Step 3 is symmetry. So we're going to put f of negative x and see what we get. So you'd get negative x squared all over 1 minus negative x squared. Negative x squared, well that's 2 negatives, so it's positive, it's just x squared. Then 1 minus negative x squared, again you just get x squared. Compare that to the original, it's exactly the same. In other words, f of negative x is equal to f of x, which means it is even symmetry. Remember what even symmetry means? It means symmetric about the y-axis. The y-axis is going to act like a mirror. Step 4 is asymptotes, and this is a huge step, unfortunately. So we have 2 types of asymptotes. The first type we'll look at is vertical asymptotes. Where do we get vertical asymptotes? We get them whenever the denominator equals 0. Well, we already figured out when the denominator equals 0. Here's the 2 points. This is why it's not in the domain, because you actually have asymptotes there. You have an asymptote at x equals 1 and an asymptote at x equals negative 1. So those are your vertical asymptotes. But remember, we want to find, sorry, it's negative 1, we want to find what happens on either side of each of these asymptotes. Does the graph tend towards infinity or negative infinity? So we need to find the limit of f of x as x approaches 1 from the left, the limit of f of x as x approaches 1 from the right, the limit of f of x as x approaches negative 1 from the left, and the limit of f of x as x approaches negative 1 from the right. Okay, ready for this? We're going to do a little bit of fuzzy math here. Okay, I've rewritten the function here so I don't have to keep going up there. So we're going to put a number just a little bit less than 1. Well, in the numerator you can actually just put 1. So 1 squared is just 1. So we have 1 over. On the bottom we have 1 minus, okay, what happens when we take a number just a little bit less than 1 and square it? If you take like 0.9999 and square it, you're going to still get a number that's just a little bit less than 1. So you have 1, take away a number just a little bit less than 1. What's that mean you end up with? You end up with a very small positive. And when you take 1 and divide by a very, 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 very small positive, what kind of number you get? You get a massive number. How big? Let's call it infinity. Okay, let's do the same thing but with a number a little bit bigger than 1. So 1 squared on the top is just 1. A number just a little bit bigger than 1, like 1.00001. If you square that, it's still just a little bit bigger than 1. So 1 takes away something a little bit bigger than 1, gives you a small negative. Okay, 1 divided by a small negative gives you a massively negative number, so negative infinity. Okay, negative 1, a little bit smaller than negative 1. So negative 1 squared is positive 1. And then a number a little bit smaller than negative 1. That's like negative 1.00001. When you square it, it's obviously positive, and it's a little bit bigger than 1. So when you go 1, take away a number that's a little bit bigger than 1, you end up with a small negative. Which means, again, just like the previous one, you're going to get negative infinity. And the last one, if you put a number a little bit bigger than negative 1, well, negative 1 squared is 1. A little bit bigger than negative 1's like negative 0.99999. If you square it, it's going to be positive, and it's going to be a little bit smaller than 1. So 1 taking away a number that's a little bit smaller than 1 gives you a small positive, and so you're going to end up with positive infinity. If it helps to picture what we already know now, let's draw two asymptotes. One of them is at 1, and the other one's at negative 1. And what we found is at 1, from the left-hand side, it's going towards infinity. But from the right-hand side, it's going towards negative infinity. And at negative 1, from the left, it's going towards negative infinity. And from the right, it's going up towards infinity. So this is already something we know about the graph. Okay, we still have another type of asymptote to go through, and that's the horizontal asymptotes. So for horizontal asymptotes, we take a look at the limit of the function as x approaches infinity, and also negative infinity. It's going to turn out that it's the same thing in this case, because if you look, you're just squaring the x's in both cases. Now, there's two ways to do this when you have a fraction, when you have a rational function. One way is you look at the degree of numerator and denominator. In this case, they're the same, x squared, x squared. Do you remember what that means when they're the same? You just take the leading coefficients, which would be 1 and negative 1 down here, and you divide them. 1 divided by negative 1 is negative 1. So we already know that the answer to this is going to be y equals negative 1. The other way you could do it, though, is you divide every term in here by the biggest degree. So you're going to divide everything by x squared. So I would have x squared over x squared, and then 1 over x squared minus x squared over x squared for this last term here. Okay, then we simplify. X squared over x squared is 1. 1 over x squared, we can't simplify that. And then x squared over x squared is 1 again. And oh, we should still be doing the limit, as x approaches infinity. So, let's do this. Well, this is just 1. 1 over x squared as x approaches infinity. Infinity is massive. When you square a massive number, it's still massive. And 1 divided by infinity is really, it tends towards 0. So you get 1 over 0, take away 1, which is 1 over negative 1, which is negative 1. So we still get the same answer. This is our horizontal asymptote. Okay, we can finally start taking derivatives and stuff because we're finding the intervals of increase and decrease. So here's our function again. We need to find f prime of x. So we're going to have to use the quotient rule. Quotient rule says to take the derivative of the top, which is 2x, and multiply it by the bottom, 1 minus x squared, minus the top, which is x squared, times the derivative of the bottom, which is negative 2x, and then we multiply divide all that by the denominator squared. So if we simplify, we can expand here. You get 2x minus 2x cubed. You can expand here. This is a negative times a negative, so it's going to be positive 2x cubed. And that's over 1 minus x squared squared. This works out very nicely because these two cancel. So what we're left with for our derivative is 2x over 1 minus x squared squared. So it's time to find the critical numbers. How do we find the critical numbers? You have to see, when does this not exist? Well, it would not exist when the denominator, 1 minus x squared squared, equals 0. Okay, take the square root of both sides. You have 1 minus x squared equals 0. Move the x squared over. You get 1 equals x squared. And then divide both sides, or take the square root of both sides and make it plus minus. You get plus or minus 1. Hey, that should seem familiar. That was our domain. We found that x cannot equal plus or minus 1, and this is why. The other thing you need to look for your critical numbers is what would make the whole thing, the whole derivative, equal 0. Well, that would be when the numerator equals 0. So that's very easy. X equals 0. So we have 3 numbers to put on our wiggle graph. We have negative 1, we have 0, and we have 1. And where we're going to plug them into is right here. Now, notice on the bottom part here, whatever we put in there ends up ultimately being squared, so it's going to be positive. So you actually only need to look at the 2x here, which means this is very fast. If I put a number above 1, like 5 in there, 2 times 5 is 10, it's positive. So this is increasing. If I put a number between 0 and 1, that's like 0.5. 2 times 0.5 is still positive, so it's increasing. If I put a negative number like negative 0.5, 2 times negative 0.5 is negative, it's decreasing. And same down here, if you put negative 2 in there, 2 times negative 2, it's negative, it's decreasing. Okay, so we can put a whole bunch of information here. For increasing, the intervals of increase are from 0 to 1 and from 1 to infinity. For decrease, it's from negative infinity to negative 1, as well as from negative 1 to 0. Maximum, minimum. Okay, there has to be a change here. Decrease, decrease. Nope, nothing there. Decrease, increase. Decrease, increase. That is a minimum. And then increase, increase, nothing there. So we have a minimum at 0. There's a minimum at 0 and a maximum, none. So all we have to do is figure out the y value of the minimum. But I think we already know that point. If we plug it in here, you get 0 over 1 minus 0. That's 0 over 1 at 0. And we already knew that 0, 0 was one of our points. I believe we found that as our x and y intercepts. And by the way, the maximum minimum, that was our step 6. Okay, time for concavity and point of inflection. You need to take the second derivative. So this was our first derivative. You need to take the second derivative. And you got to use the quotient rule again. Quotient rule says to take the derivative of the numerator, which is 2, and multiply by the denominator, 1 minus x squared squared, minus the top numerator, 2x, times the derivative of the denominator. So the derivative of the denominator, it's the chain rule. You have to move the 2 down and keep the inside the same, the 1 minus x squared. This 2 drops down to a 1, so you don't need to put it. And now you need to multiply that by the derivative of the inside here. And the derivative of the inside is negative 2x. Plus, we need to divide by the denominator, 1 minus x squared squared. We have to square that, and that's our derivative. Okay, time to simplify. Don't expand this. I see another 1 minus x squared here, so this is going to be something we factor out actually. So I'm going to leave that. And what do I have here? I have negative and negative, so it's going to be plus. I have 2x times 2 times 2x. 2x times 2 is 4x times 2x is 8x squared. And I still have the 1 minus x squared. All over 1 minus x squared. Now, it's squared, squared. You're going to multiply those, you're going to get to the fourth. Let's take out a greatest common factor. We can take a 2 out, and you can also take out a 1 minus x squared. That's the greatest common factor. What do you need to multiply this by in order to get this right here? You need to multiply by another 1 minus x squared. What do you need to multiply this by in order to get all this? You just need to multiply by 4x squared. And that's all divided by 1 minus x squared to the fourth. Hey, we've got a 1 minus x squared here and 4 of them here. Let's drop that down to a 3. So we've got 2 times 1 minus x squared plus 4x squared. We can combine the negative x squared and the 4x squared and get 3x squared. So we get 1 plus 3x squared all over 1 minus x squared to the third power. So we have to get our pips now. We got to figure out what are the potential inflection points. And we're going to do that by doing the same thing we did before. We want to see, when does this not exist? Well, it would not exist when 1 minus x squared cubed equals 0. Okay, take the cube root of both sides, and you'll have 1 minus x squared equals 0. The cube root of 0 is 0. Move the negative x squared over. Hey, this looks familiar again. Take the square root of both sides. X equals plus or minus 1. So those are your 2 of your pips. To get the other pips, you want to know, when does the numerator, when's the whole thing equal 0? And the whole thing would equal 0 when the numerator, 2 times 1 plus 3x squared, when does that equal 0? Well, divide both sides by 2. You're left with 1 plus 3x squared equals 0. Move the 1 over, so 3x squared equals negative 1. Divide by 3. X squared equals negative 1/3, and then take the square root. So I'm actually going to write it here, negative 1/3 plus minus. What do you notice? You're taking the square root of a negative. You can't have that. So there's no more pips there. The only pips you have are plus and minus 1. So those are the numbers that you're going to put on your wiggle graph. And we're going to test those right here. You don't have to worry about the 2, by the way, because that's obviously always positive. So this is also always going to be positive. So whether you put positive or negative in here, it's going to be positive. Times 3 is still positive. Plus 1 is still positive. So you know this is going to be positive up here. So for all of them, we're going to have a positive divided by something. So let's try 10 in here at the bottom. 1 minus 10 squared is 100. So 1 minus 100 is negative, and a negative cubed is still negative. So we're going to have positive divided by negative, which means negative. This is concave down. Okay, easy between negative 1 and 1, try 0. So 1 minus 0 is 1, 1 cubed is 1, which is positive. Positive divided by positive, positive. It's concave up. And something less than negative 1. Let's try negative 10. Negative 10 squared is 100. 1 minus 100 is negative 99, and a negative number cubed is still negative. So we have positive divided by negative, which is negative. This is concave down. So now we can do our concave up, concave down, and inflection points. Concave up from negative 1 to 1. Concave down from negative infinity to negative 1, as well as from 1 to infinity. Inflection points. Remember, you look to see where it changes signs. So from negative to positive, looks good, and from positive to negative. You want to write both those down as inflection points, right? No, you don't. I'm telling you there's none. Why would that be? Because if you go all the way back to the start here, you'll see that the domain tells us that the x cannot equal plus or minus 1. They're not in the domain at all. So those are not inflection points. And I'll write that down for you. Not inflection points because they're not in the domain. All right, we're now ready to graph this thing. Remember, we had asymptotes at positive 1 and negative 1. Vertical asymptotes, I mean, at plus 1 and negative 1. And we also had a horizontal asymptote at y equals negative 1, so we need to include that on there. Now, other points we had was our minimum at 0, 0, which was also our intercepts, of course. And that's it. We have no other points to work with. But remember, we also have this information right here. We said that it was going to have this shape right there, so we can add that into our drawing. Okay, now it says it's concave up from negative 1 to 1, and we also know this is a minimum here. Well, to keep it concave up, can you see it probably looks something like this? And if we check the increase and decrease, it says it's increasing from 0 to 1, and it's decreasing from negative 1 to 0. Decreasing from negative 1 to 0, yep, that's decreasing. Increasing from 0 to 1, yep, that's increasing. So that looks good. Okay, let's look below negative 1. Below negative 1, it should be concave down the whole time, and below negative 1, it should be decreasing the whole time. So the whole time, it has this sort of shape right here, and you can see it should get closer and closer to that horizontal asymptote, but never reach it. So that looks good. How about greater than 1? It should also be concave down, and it should be increasing. So increasing and concave down the whole time would look something like this. We've done it. We've drawn our graph. A couple checks we could use here. We could look to see whether our symmetry worked out. We said that the symmetry was going to be even symmetry. It should be symmetric about the y-axis. Should reflect over the y-axis. Yep, I haven't drawn it great, but if you had a perfect drawing and reflected over the y-axis, it would definitely be like a mirror copy. Want to see the actual graph? And there it is. Again, looks pretty close to each other, doesn't it? Perfect? No, but pretty good approximation of the graph. So we've done it, and not a moment too soon.